Today's lesson is all about segments. So let's get started. First, let's talk about definitions, postulates, and theorems. Definitions, theorems, and postulates are the building blocks of geometry proofs. And geometry proofs are something that you're going to be doing throughout the year. So it's important that we know what those mean. So a definition defines or explains what a term means. It can be written as a conditional statement in any direction, which means it can also be written as a biconditional statement because it can go either way. Definitions are used in the reasons or justification column of a proof. An example of a definition would be a midpoint divides a segment into two congruent parts. So that describes what a midpoint is. So here we have a little mini proof on how this works. So we are shown that this line segment is here, and for the first proof, we are given that M is the midpoint of line segment AB. And so if we want to prove that line segment AM is congruent to line segment MB, we would simply first state what we were given, that M is the midpoint, and then we would use our definition of the midpoint to conclude this. And you'll notice the way it's written is a little important here, because on the second proof, we're given the other one. We're given that line segment AM is congruent to MB. And we want to go backwards. We want to prove that M is the midpoint of line segment AB. Again, we start with what we were given, which we were given that part here. And if you look, it's really just the reverse of our definition in part 2 from the first mini proof. So definition of a midpoint can really go either way depending on what you're given in a proof. A little confusing, but we're going to be working with proofs pretty much daily in every class, so you'll get the hang of it. It's hard, but you're going to keep trying through it. Okay, so theorems and postulates. Theorems and postulates are statements of geometric proof. Postulates are assumed to be true. Theorems are really proven based on postulates or already proven theorems. Take, for instance, the Pythagorean theorem. Okay, the Pythagorean theorem came about because it was a theorem that people used known postulates and just known geometric facts to prove that. Okay, we don't have to keep proving the Pythagorean theorem. We can just state we know the Pythagorean theorem is true. For this class, you just need to know that theorems and postulates, we're going to think of those as one group. Really, you don't need to prove a theorem unless it's a new theorem, and that really happens when you get into higher math and you talk about like people who are getting their doctorate in math and are trying to defend their theory. Okay, so for this one, we're going to kind of think of those as two of the same group there. So examples, all right angles are congruent and all radii of circles are congruent. Okay, so those are just assumed to be true right there. Okay, those two can be used in a proof, and here's a little mini proof. So if we're given that angle A and angle B are right angles, we want to prove that angle A is congruent to angle B. So again, we're given that, well, since they're both right angles, we can assume by a postulate that if two angles are right angles, they must be congruent. All right, so now let's get into segments. And the reason we had to talk about definitions, theorems, and postulates is because our first thing is the addition segment postulate. It says if B is in between A and C, then the length of AB plus the length of BC equals AC. And you can see that they can reverse it as well. So here is a drawing. I'll put that here. So here's line segment AC. And we see that AB right here, and then BC, if we add those two together, we would get the entire length here. Okay, and so we can see that that is a true geometric statement there. And so an example of that would be, you have line segment A, let's do D, F, and let's say you have E right in the middle there. Let's say this line segment is 7, so D, E equals 7, and let's say EF equals 3. Then we conclude that DF is equal to 7 plus 3, which is 10. So that's a short, very basic example of the angle addition, or the segment addition postulate, and we can see that we're going to be using that quite often. Makes sense there. Okay, we have a midpoint too. So kind of the same thing as your builds off of your angle addition postulate, segment addition postulate. I keep mixing that up. So our segment addition postulate, Only the difference here is our midpoint, let's call that M, okay? That's going to give us two congruent line segments. So line segment AM is going to be congruent to line segment MC because M is the midpoint, and we do have, still true, our angle addition postulate is still true, although these two would actually be the same measure there, okay? And so, you know, that's going to be true regardless. As long as you have a midpoint here, you know that it is cutting it in half. So a bisector is any point, line, ray, line segment, or plane that splits another figure into two congruent parts. So technically, the midpoint is a bisector because it's a point that splits it in half. But you could also have a line segment or a line or a ray. Here's a ray, or we could make that a line, and this line would be called a bisector because it's cutting another figure in half. Okay, so a figure is a bisector if it does that job there. A couple things to watch out for. You'll see that in all of my writings here, I'm very particular about what I'm actually writing. So when you're talking about lengths, like length AB, the length of line segment AB plus the length of line segment BC is really equal to the line segment of AC. Notice I did not put the little line above those two letters because I'm talking about their lengths. Okay, so this really signifies length. And when you're talking about lengths, you want to use this equal sign. When you're talking about the figure, so when you're not talking about the length, but you're talking about the figure as just a geometric shape, or if you will, that's when you want to use the line segment, or the congruent, sorry, and then the line segment bar across the top. And here, well, you really wouldn't use the addition postulate, but that's okay. And so you would have this. What you would really use with this, you really wouldn't put it in an equation. A better use would be like your midpoint. And so this is where I put that, because that signifies we're not talking about the length necessarily, like a number or an expression. We're really talking about the actual line segment that we see. Okay, so you need to be careful that you're not, interchanging those two. It's going to become important when we do our proofs. Okay, you cannot use the congruent symbol when you're talking about lengths, and you cannot use the equal symbol when you're talking about line segments. It's just all in the way that we write things in geometry. So that's something you're going to need to watch out and be careful with. And we're going to do a little activity about next week that we're going to talk about what are some ways that we can remember those.